Thank you for the introduction. Like you said, I'm Nicole Chung. I just finished up my first year teaching over at the Thatcher School, just an hour away in Ojai. And the title of my project is Understanding the Stability of Active Layer Materials in Organic Solar Cells, which I'll abbreviate as OSCs. And my mentor is Sang-Chul Yu. Okay, so before we talk about organic solar cells, I think it's important to wrap our head around just how big the problem is of the global energy crisis and the need for renewable energy sources. So every day on Earth, we are consuming about 14 terawatts of energy globally. That's equivalent to if we had 3 planet Earths and each person had their own 60-watt light bulb and was powering it for 24 hours, just to give you a scale. But unfortunately for us and all the fossil fuels we use, that's equivalent to a ton of CO2 emissions. So about 16.4 billion gallons of gas, 162.8 billion pounds of coal, or 336.1 billion barrels of oil. And if you want to ever do an equivalent graph like this, you can use the Department of Energy website. Super convenient. Meanwhile, we have the sun, which is continuously supplying us with 85,000 terawatts of energy globally. And that's taking into account things like reflectivity and scattering, because obviously not all of the sun's rays are being absorbed by the Earth. So if we have over 6,000 times the amount of energy we're consuming powered by the sun, what makes it so hard to harness that energy in an organic solar cell? When we look at solar cell technology today, we've come a really long way since the first invention of it in the 1950s, but we still have ways to go when we look at all different types of energy sources. So as you can see, non-renewable energy sources like nuclear, natural gas, and coal still have a lot on solar cells in terms of their efficiency. The highest ever reported solar cell efficiency was actually in multi-junction cells. That's when you kind of have multiple cells working in tandem. That came close to 50% about 4 years ago. And the most recently reported highest efficiency rate in organic solar cell was actually 19.31%, reported just earlier this summer in Hong Kong. So if we have such kind of limited efficiency with solar cells and even more limited efficiency with organic materials, why do we even care about studying them in the first place? So if we look at the structure just on a really small scale of what an organic semiconductor looks like in comparison to its inorganic counterpart on the left there, you'll see silicon, which is a really commonly used material in solar cell industries, has a much more crystal structure. So it's much more orderly, and it has that beautiful lattice structure. Whereas on the right, we see that with an organic material, it's much more amorphous. It's a little bit more messy. It's a little bit more unpredictable in terms of its properties. But even though those properties are a little bit less predictable, it's pretty easy to measure them, and it's much, much cheaper than things like silicon and other inorganic metals. So we love the low cost, we love the tunability and the flexibility that these organic materials can provide. As you can see here, this is an example of a flexible solar cell. You can see how much it bends. And we also like how it's light, pretty low molecular weight in comparison to metals. When we're talking about organic materials, we're going to talk about 2 types of things: electron donors and electron acceptors. So what constitutes a good donor is a large organic polymer with good sp2 conjugation. And for those who might not remember or have never taken organic chemistry, conjugation just means that you have your double bonds aligned in such a way that they're able to share electron density across pi orbitals. Whereas on the figure on the right there, you'll see if you have a little carbon atom in the middle, sp3 hybridized, that's interrupting those double bonds, they can't share as well. So we like our good conjugation in an electron donor. And in an electron acceptor, we prefer small molecules with high electron affinity. So they like to take those electrons from the donors. And typically a really commonly studied class of acceptors is called fullerenes. So you might think of carbon-60 or buckyballs. You can see they have a nice sphere shape with a lot of good conjugation. But we're also going to be talking later in this presentation about non-fullerene acceptors, which is a material I worked with this summer. So when we think about how we put these donors and acceptors together in an OSC, you might look up an organic solar cell on Google and it'll tell you you have an electrode on the top, electrode on the bottom, and you might have like the donor and acceptor layer just perfectly sandwiched in between. But we've done enough research to know that that perfect discrete levels of acceptor and donor is not actually the most efficient way to create a solar cell. What is actually preferred is something called a bulk heterojunction cell, which is pretty much a fancy way of saying that your donor and acceptor material are going to be intermixed in the active layer, as you see there. So the first step in the mechanism is obviously we have our sunlight. Different materials prefer to absorb different wavelengths of light, and the materials we work with usually prefer UV and visible light, specifically around the blue-green range. And what happens on a tiny, tiny scale when we have this excitation from sunlight is that we're exciting electrons from the valence band into the conduction band. What does that really mean? Well, it means that an electron is hopping from really close to the nucleus into somewhere farther. And what it leaves behind in its wake is something called an electron hole, as you can see there in blue. And this electron hole is really just the absence of the electron, and it has this positive charge that is really attracted to the electron that is now left it. It's a little bit of a confusing concept because it's not actually a physical particle. In an ideal world, this exciton is then going to separate. Those electron holes can migrate through the donor material and be attracted to the anode because they're positive, while the free electrons can migrate through the acceptor material all the way to the cathode. And of course, this is in a perfect solar cell world. In the real world, we are limited in the efficiency of this process because these charges are electrostatically attracted to each other. We run into this issue called charge recombination a lot in the active layer of a solar cell. And that issue can be combated by things like testing different donors and different acceptors, creating them in different ratios of blends and things like that. So what is the research in our lab accomplishing? So typically we'll test materials that can either go into flexible cells or semi-transparent cells. These have a ton of different applications. Flexible cells are a really interesting thing to architects who want to design windows of very different colors. You need good tunability of the organic solar cell in order to create such a beautiful colored window. And semi-transparent cells can be used in things like car windows. Mitsubishi is a company that's been working on OSCs for a long time, seeing how can we use this maybe in a car. And what we do then is morphological characterization on a nanoscale level. So some people in our lab are doing FTIR, UV vis, atomic force microscopy, conductive AFM, and things like that to characterize what are the properties of these materials we're going to use. And the data we eventually get from that is three-pronged. It can tell us things about the efficiency of the solar cell. So for example, you could use a JV power curve to see how well your cell performs. You can evaluate the costliness of a material. So if I use these things in different ratios, how expensive is it compared to an inorganic one? And then you can also measure stability of an OSC. So how long does this last? How resistant is it to deterioration by heat? And that's really going to be the goal of my project. So my research question for the summer was, what is the glass transition temperature, or the TG, of CoTIC-4F, which is a non-fullerene electron acceptor? And what are the implications of this work for OSC stability overall? So this is the chemical structure of CoTIC-4F. As you can see, it has a very long name, so that's why we abbreviate it. And it has a pretty big molecular weight. And as you can also see, it looks nothing like a fullerene acceptor, which, as we saw before, was those spherical buckyball type shapes. And the reason why we want to work with an NFA is because, first of all, they are very poorly studied in the literature. We have already some data about the TG and the heat stable properties of fullerenes, but there's not a lot reported about things like CoTIC-4F or other NFAs. And also, these types of molecules that have this beautiful symmetry and a lot of tunability are preferred for things like flexible OSCs, where we want to be able to adjust the energy levels and create pretty colors and things like that. So what is the TG? It is a very important metric of stability and can dictate the mechanical properties of polymers. I recently learned that a fun example of this that you could find in your kitchen is actually peanut brittle. So when you're creating this candy and it's this kind of syrupy, sugary thing, that's considered a rubbery polymer, whereas when you cool it down, it becomes hard and brittle. That is an experience of TG in food. And as you can see on this graph here, it's a pretty simple way to evaluate, as the temperature of a polymer increases, how is its physical state changing. So the TG is the point at which we transition from this glassy state, or a hard and brittle state, to a rubbery and flexible region above TG. And you can see here, this is just a simulation of what the polymers look like at TG, but you can see in those top two pictures there, you have more space between polymers to to transport electrons, whereas above TG, we see that they aggregate together a lot more. And this is going to cause poor morphology in the active layer of the OSC and less good electron transport. So ultimately, we want a material that has a high TG so that it's stable at a higher range of temperatures before it kind of becomes this rubbery flexible thing. So to go over the methods a little bit, the first important thing that pretty much everyone in our lab has to do is substrate preparation, because no matter what material you're working with, you're going to have to deposit it onto something. So in our case, that's usually glass. You start by cutting the glass into usually 8 to 10 pieces, however many samples you want to test. And then you rinse that off with some detergent, and then you go through 3 rounds of cleaning in the sonicator. So we first start with deionized water, then do acetone, then do IPA or isopropyl alcohol for 20 minutes each. And once that's all done, we can dry that overnight in the oven. And while that's drying, we can make our solution for our desired concentration. It might be just the electron donor, it might be the acceptor, it might be a blend of these two. And then we can let that stir overnight. In my case, it was 60 degrees Celsius, but you just want to choose a temperature that's below the boiling point of your solvent. Next, we have the fun part, spin coating. Once you have your solution made and your substrates dried, the next day you can go in and essentially pipette your solution onto the substrate, and then you press the on button and the magic starts happening. So there's a lot of adjustable parameters that we start introducing experimental variability into the procedure at this point. So one thing you can vary is the RPM, or how fast it's going, the duration of time that it's spinning for, the ramp time, so how long it takes to go from 0 to 1,000 RPM, and then your solution concentration. And all 4 of these parameters are really going to affect the thickness of your layer. So as you can see on the right there, that's an example of what a good testable substrate would look like. It took me weeks to get there. But if I wanted to measure the thickness of those, that's going to dictate how well they're going to absorb light. And the last thing you can vary is the environmental conditions. So when I was training to use the spin coater, I was starting off in the fume hood exposed to ambient air, but ideally you want to be working in the glove box, which is only exposed to nitrogen with very trace amounts of oxygen and moisture. So then we get to the fun part where we can start measuring the properties of these materials. So profilometry is a pretty simple technique, but with very powerful results to show us the thickness of what our layer is. So all you have to do really is take your substrate, create a small scratch across it, and then run it through the profilometer, which will basically put this little stylus tip perpendicular to your scratch to evaluate what's the difference between the scratched glass and the unscratched part or the coated part. And you take multiple trials of that, usually 3 or 4, and you can average them together to find the thickness. And what the computer shows you over there, that little V curve, is literally just showing you the glass at the bottom of that V, and then the lines on the side are showing you the evenly coated film. And you just can manually go in and see what's the thickness between these 2 layers. And it's important to do this across all of your samples because it can ensure you have consistency across all of them. So if I use the same spin conditions on all 4 of these substrates, I want to see a thickness of, say, 85 to 90 nanometers. And if I saw an outlier like 100 or 75, I might not want to use that substrate. So now, where I spent most of my time in the lab this summer was doing UV vis to measure the absorbance properties. And how a UV vis spectrometer works, you basically just have 2 lamp sources that give you your UV invisible wavelengths. They're filtered and then go through a monochromator, which aims your broadband of wavelengths in a very narrow line at your sample. And in my case, I wasn't working with a cuvette because I was working with just a piece of glass, and the machine has a holder for that. And your data readout will look something like that on the computer, which is basically just doing Beer's law at a ton of different wavelengths. And the general principle is if you know how much current is going in and how much is going out, you can figure out the absorbance of material. And another important step in UV vis is to always calibrate your machine using just a blank glass substrate so that you can account for the fact that glass also absorbs UV vis light. So how does this actually help us to determine the TG? This is a pretty novel method of figuring out the TG. It was established in 2017 in a paper, and this is in contrast to other methods like differential scanning calorimetry that sometimes can only detect a very weak signal of TG. And this can also be used in a pretty low-tech way. You really only need a heater and a UV vis to be able to do this method. So the first thing I did after I calibrated the machine and took the UV vis at room temperature is I began to anneal the film. So that's just a fancy word for heating, where you put your substrate on the heating machine for 10 minutes at a time at different temperatures and take the UV vis at each increment. So usually I'm working with a temperature increment of 10 to 20 degrees Celsius, measure the UV vis, turn the temperature up, do it again for a variety of temperatures. And once you've done all the temperatures and collected all the UV vis data of what you want to see, you can then put that into Excel and see a composite graph of all of your spectra. And what's important to do at this step is to normalize the data to be able to actually have a fair comparison between all these different temperatures and the absorbance you're seeing. And finally, the fun part, actually extracting the TG from this data. Essentially what you're seeing here on the y-axis, the deviation metric, is just the fancy way of putting what is the difference between all of the points on our reference curve and all of the points at each temperature's curve above it. So for the 40 degrees point, you'll see it's calculating what are the overall deviations between our room temperature and 40 degrees. For 50 degrees, what's the difference between room temperature and 50 degrees, and so on and so on. And essentially what you start to see in this example is that at 65, our trend line drastically changes into a really, really steep deviation from room temperature. And the point at which these two best fit lines intersect is our glass transition temperature. So what did I find in my results? This is the raw data, so this has not yet been normalized, but you can still see just kind of qualitatively what's going on here. The first thing that's pretty obvious is that at temperatures above 150 degrees Celsius, we saw a super steep decrease in the intensity of the absorbance of the material. So complete loss of the integrity of these peaks. And then also at 120 and 130, that's still a pretty sizable gap between all those other peaks that come above it. And then when we normalize this data, which is kind of giving us the meaningful data, we can see these trends again. We can see that above 150 degrees, we get this just kind of huge curve, much broader. And then at 120 and 130, we also start to lose that first shoulder that seems significant. So because these are deviating so much from the signature absorption of this material, that means we actually ended up excluding a lot of these temperatures above 120 degrees for doing that final TG calculation. So when I did calculate the TG, I was able to find my best fit lines where they crossed over. That came at about 76.9 degrees Celsius. And as you can see on the x-axis, I had to exclude everything above 120 degrees. But this is the result of about 7 or 8 data points total, I think. And when I started out this process, I used far less data points than that. So the more data points you have in a graph like this, the more accurate your temperature will be. So what does this data actually mean? I got this TG of 76.9 that I measured. I also did the profilometer, which measured a thickness of about 93 nanometers. Unfortunately, this information isn't super useful if you're not comparing it to anything. So I did have a few other substrates of Cotic4F that I was going to measure the properties of, but unfortunately, I didn't take a full spectrum of the UV vis, so I had to throw that data out. But further trials in the future, if this procedure was repeated, would help verify the reproducibility of my data and also if this method is any good. If we started getting some results that were super different from this, maybe we would question the method. And then also future studies in the lab are looking at the effect of crosslinkers. This is Sangchul's thesis and also some graduate students are going to pick up the work. Looking at the effect of crosslinkers in the active layer. So some studies have shown that if you add a crosslinker to this part of the solar cell, you can get a higher power efficiency because you're stabilizing its heat stable properties, I guess. And so having a baseline of these measurements can maybe see, okay, if they add a crosslinker to the acceptor of Cotic4F, how does that change the TG and the thickness, et cetera. So when I thought about some of the classroom connections that I could use from this summer, my brain went in many directions. I thought about maybe clean energy, Excel data plotting, what's the significance of UV vis. But ultimately, I think what stood out to me this summer was the importance and the versatility of polymer science, which is always expanding in new ways. And then also just this iterative process of you heat something up, you observe the properties, you see the changes, what are you going to change next time, and how does that build on your theory? And I think introducing students to those concepts earlier is better. So I realized I already had some polymer interest and scaffolding in my classroom. Recently, I started a molecular gastronomy class this past spring, and students were asked to research different ingredients that go into vegan burgers, like strange soy proteins and pea proteins and things like that. And some of the materials they studied were polymers. So carrageenan is a common red seaweed extract. I had one student researching xanthan gum, which is used in a lot of baked goods and even gluten-free things a lot. And then I had also a student go so far as to make some vegan caviar using sodium alginate and calcium chloride, which is actually a cross-linking reaction. So I realized I already had some interest. I already have some tools to work with. So how can I translate this into a more experimental setting with more quantitative data? And one idea I came up with, a sort of common theme I see in all of these things, is their ability to emulsify foods, which is a really important thing we need in anything from dressings to baked goods. And so one idea I have is that you could add polymers like alginate, carrageenan, agar, which are all seaweed extracts, by the way, to an emulsion, say of oil and water, observe qualitatively what the best stabilizing agent is, then get more into the quantitative side to measure the effective heat on this process. So if we were to heat up oil and water, heat up a polymer, how would that make the emulsification better than if we did it at room temperature or at a cold temperature? And then to evaluate and predict how chemical structure could agree or disagree with these results. So I think high school students are completely capable of understanding organic structure. I've tried it before, and it's actually really fun for them once they get the hexagons and everything. So I think it could be super fun to incorporate that molecular bit as well. Many thank yous are in order to the Nguyen Lab for hosting me. I learned so much from all of you. Sangchul for being an amazing mentor, and Sam and Huang for helping out along the way. Frank for your kindness and thoughtfulness in coordinating this program. Bill, Laura, and Marilyn for feedback every single week, and the MRL and UCSB for making this opportunity possible. I'm very grateful. Thank you.
Questions? Impressive that how much you learned from last 6 weeks. I have a couple of questions. So the first one is about so you play around to fit the baseline fit, right?
Yes.
So how much deviation that you see? So you said that the TG is 76.9. You have like the plus minus how much?
Yeah. So essentially, there's a lot of variability you can use to create this graph, because I can say to Excel how many points I want to include in that orange line and also how many points I want to include in that gray line. So if I included more in that gray line, I probably would have seen a shallower thing and then a shallower TG, and the opposite effect for the orange line. So I really just ended up going by what the R squared values were telling me to like find the best ones of those, and then seeing this data. But I would say it could be plus or minus like 10 degrees in either direction, depending on which points I used, which is pretty significant.
The second question is, you see the very strong dependence on how wide the spectrum you take. So like for now you take it from like 300 to
1500, yeah.
So if you're narrowing down, will it be derived a lot from that? Just give the kind of your prediction.
I feel like more is better. More is always better for the data points, but it depends on the different materials. Like some of them don't absorb that many wavelengths. So yeah, I'm not sure.
And the last one is so I think in the very beginning of the introduction slide, so you mentioned that the human is using 14 terawatt. So I think terawatt is the power
Yeah, so terawatts is the unit of energy, terawatt hours is the unit of power. So I had to go through a lot of like figuring out some calculations to go from energy to power and figure out some of those numbers. But usually, yeah, you do see those numbers reported in power more often than energy.
So that means human use 40 terajoule every second.
I trust you on that. I believe it. I believe it. Yeah.
And excuse me, on the subject of the TG, it's 77 to me. Oh, that's pretty hot. But if, for example, if this was in a solar material on a rooftop, is that good enough? It can get pretty warm up on a rooftop, right? I mean, it might. Do you have any thoughts on that?
Yeah, so I was looking up a lot of the TG data, and actually one thing I didn't talk about, but I could go on for about a while, is glass transition temperature is actually not a singular temperature for a material. It's a range of temperatures, unlike something like a melting point, for example, in a crystalline solid. So first of all, there's variability. Like if you were to do this measurement over and over again, you would see variability and that would not be weird. But a lot of polymer materials, I think I saw in general that they had lower TGs than a lot of the acceptors do. I'm not sure why that is, but the higher the better is the name of the game. And I'm not sure, maybe, 100 plus would be the goal, maybe, but I would not say this one is like bad.
That obviously that temperature code of 4F is not changing. It's just the gaps, like you were saying, and so the UV vis will just have more. There'll be more absorbance due to that. It's interesting. Okay. Just one more question is that this classroom idea with the emulsification. What kind of, will that be a qualitative test in terms of how that feels?
I mean, it's just a seed of an idea, but I
Yeah.
think one of the cool things about just mixing oil and water and doing things like solubility is you can just see it with your eyes. Usually you can see an effect, but then we can add metrics like heat and I don't know, maybe some other types of technology can help us see more on a molecular level what's going on. But I think a mix of qualitative and quantitative would be my goal. I would kind of need to see how much stuff we have available in the lab.
Yeah. Well, that's a fantastic presentation. Thank you. Thank you, Nicole.
Thank you.